Hello everyone, this is Mrs. Lim, your physics teacher. Okay, this is the first part of magnetism. In this video, we will be covering what are the properties of magnets. Okay, and then we will talk about induced magnetism as well as what are some of the methods of magnetizations of your magnetic material. Okay, so these are the learning outcomes. Okay, so let's move on into the first property of magnets. Okay, the first property of magnets is that magnets, when left freely suspended, it will always come to rest in a north-south direction. Why will it always come to rest in a north-south direction? This is because you can imagine that the Earth, okay, is like a huge magnet at the center of the Earth. And in the center of the Earth, at the geographic North Pole of the Earth, the North Pole of the Earth, it is actually the south pole of your magnet at the center of the Earth. It's the magnetic, it's the south pole of the magnet in the center of the Earth. So this south pole will forever attract the north pole of a freely suspended magnet. So the north pole of a freely suspended magnet will always point towards the geographic north pole, and the south pole will similarly point to the geographic south pole. Okay, this is also the reason why compass will always point in the same direction. So your compass is actually a freely suspended magnet, okay, with a north-seeking pole and a south-seeking pole. So the north-seeking pole will always point to the Earth geographic north. Okay, the second property of magnet is that magnets always have two poles, the north pole and the south pole. Even when the magnet is being broken or divided into many pieces, okay, each of the pieces will still have a north pole and a south pole at its end. Okay, the third property is that the poles will be the strongest, okay, magnetic effects, have the strongest magnetic effects at the poles. And like poles repel, unlike poles attract. This is the most important rule of magnet. Okay, and lastly, magnets are able to attract magnetic material. And so whenever there is attraction, we can't tell if the material is a magnet or it may be an unmagnetized magnetic material. But repulsion will only occur between two magnets. Okay, so next, this is a flow chart to determine if an object is a magnet. Okay, if an object is a magnet. So first step, you move one end of a magnet near to the object. If the magnet is repelled by the object or the object repelled away from the magnet, then it's very obvious only magnets and magnets will have repulsion. So the object must be a magnet itself. If the object and the magnet attracts, then so there is another case. If the object and the magnet does not attract, so the magnet does not attract the object, then obviously the object must be a non-magnetic material. But if there is attraction, then there could be two possible scenarios. Okay, it could be the magnet is made of, the object is made of a magnetic material, or the object itself could be a magnet. So how do that determine that? So I move the other end of the permanent magnet or near to the object. If the magnet is repelled from the object, okay, so there is a repulsion, then the object must be a magnet. But if the magnet is still attracted to the object or the object is still attracted to a magnet, then the object must be a magnetic material. Since both ends get attracted to a magnet, that means that it doesn't have like poles, there is no repulsion, the object must be made of a magnetic material. Okay, so how do I remember what are magnetic materials? I need complete silence. Okay, so the four magnetic materials are iron, nickel, cobalt, and steel. Okay, I need complete silence, the first letter of each one. Okay, so these are the only four magnetic materials that you will learn in your syllabus. Okay, so recap a little bit. If metal A and metal B attracts, okay, one of them must be a magnet and the other one can be a magnet or it can be a magnetic material. Can't tell. Okay, but if A and B repel away from each other, then it is very sure that both A and B must be magnets. So repulsion is the only test for magnetism. Okay, next, let's take a look at this question. The ring magnets are found to be floating on top of one another. Why are they floating? Okay, this is one of the possible reasons. Okay, you take a look at the top magnet and the middle magnet. The south pole are facing each other, so the light poles will repel. Similarly, for the bottom magnet and the middle magnet, the north poles are facing each other, so again, light poles repel. So the answer is as follows. The surface of the ring magnet facing each other have light poles. I do not know whether they are north pole or south pole, so I just say in general, they have light poles facing each other. And you must mention about the properties of magnet, which is light poles repel. Therefore, the rings will repel away from each other and will float on top of one another. Okay, next, over here, I have a few materials. Okay, I have a material with an NAB, and another material with an NCD, and another material with an NEF. So AB, CD, EF, three different materials. Okay, you need to identify for me whether they are magnets or magnetic material. And if they are magnets, what are their polarities or what are their poles? Okay, whether Na is a north pole or a south pole, etc. Okay, you may pause the video now to think about the answers to this question. Okay, I'm going to go through now. So, how do I come about doing such questions? The first step and the easiest way is to look for the repulsion, because repulsion means that both objects must be magnet. So over here, you can take a look at the one repulsion. With repulsion is the one in the middle. So repulsion is happening between DC and AB. So it is very sure that this material, DC, and this material, AB, must be magnets. Okay, both of these must be a magnet. Okay, so then I come over to here. Okay, then let's work out one by one. Okay, if the south pole attracts the C, attracts the side C, and C must be a magnet, so C must be a north pole. Okay, and then over here, AB, I know AB must also be a magnet. If there's attraction between C and B, B must be a south pole. Okay, and then after that, you take a look at E and F. Okay, E and F, when I switch the side AB and DC, okay, A is having a south pole and D is having a north pole. Okay, so that when I have a north pole and a south pole that brings near to E and F, or I bring near to side E, you will see that there is still attraction. So E and F must have been a magnetic material. So the answer is as follows. Okay. Okay, then we move on into what is induced magnetism. Okay, so what happens for induced magnetism is the same as induced charges. Induced magnetism only happens when you bring a magnet close to it. So for example, you take a look at this. Okay, I have a magnet over here on the left-hand side, and I have an iron bar that is brought close to the magnet. Okay, I do not need to touch. Magnetic induction can happen without physical contact. Okay, I just need to bring close to it. What is going to happen is, with this magnet nearby, this permanent magnet nearby, this north pole of the magnet will actually induce a south pole on this magnetic material, this iron bar. Okay, this iron bar over here. Okay, so because of this north pole nearby, I will induce a south pole here. So this iron bar becomes what we call an induced magnet. It behaves like a magnet now because I am near to this permanent magnet. But if I were to remove this permanent magnet away, this iron bar will lose its magnetism. It will no longer behave like a magnet. It will just be a magnetic material. Okay, so when it becomes an induced magnet, so this one will behave like a magnet. It will continue to attract other magnetic materials. But just take note that induced magnetism can only take place when a magnetic material is placed close to a strong magnet or within a current carrying solenoid, which we'll talk about it later. But it will only work for magnetic material. So what do I mean by that? If I were to put my permanent magnet close to this material over here, then this material is not an iron bar. Let's say it's a plastic bar. Okay, you know that plastic is a non-magnetic material. So this plastic bar will never ever become an induced magnet. Okay, there will never be an induced south pole on the side nearer to the north pole. Okay, so it only works for magnetic material. Okay, so it's also the way of explaining why the iron bar gets attracted to the magnet when it's placed close to the magnet. Okay, you don't mention, oh, because iron bar is a magnetic material, so it gets attracted. Okay, whenever the question asks for why is there attraction, why is there repulsion, remember you always need to go back to the properties of magnets, which is like poles repel, unlike poles attract. So why did the iron bar get attracted to the magnet? Okay, it must have unlike poles. And how come, where did the unlike pole come from? It must come from induced magnetism. Because the magnet is nearby, I will induce an opposite pole on the side nearer to the magnet. And because unlike poles attract, therefore, the iron bar gets attracted to the magnet. Okay, this should be the correct way of explanation. You need to mention about induced magnetism. Okay, so the similar one over here, you can see that I have a permanent magnet. When I bring close to a paper clip, you see a lot of paper clips gets attracted to it, and some of the paper clips will be dangling downwards. So what happens is each of this paper clip becomes an induced magnet. So it behaves like a magnet. It will in turn be able to attract another paper clip below it. And then when it attracts another paper clip or this paper clip comes near to it, it becomes again an induced magnet, and therefore it's able to attract furthermore paper clips. Okay, so take a look at this again. Magnetic induction is the process whereby an object made of a magnetic material becomes a magnet or behaves like a magnet when it is near or in contact with a magnet. Okay, I don't need to be in contact, I can be near as well. Okay, obviously in contact, obviously it will become an induced magnet as well. Okay, so over here, so you have this permanent magnet, bring close to this soft iron bar, or even touching this soft iron bar, then this soft iron bar becomes an induced magnet. Okay, okay, so over here, like you will always ask, so when you bring a magnet close to paper clips, why are the paper clips attracted to the magnet? Again, I repeat, do not say that the paper clips are made of magnetic material, it gets attracted. I do not want that. Attraction means I need to see unlike poles somewhere in your answer. Okay, so what happens here is when my magnet is brought close to the paper clip, I will induce poles. Okay, or I will induce magnetism in my paper clips. The induced poles will be as follows. Okay, it will induce opposite poles. So this side will be north pole, this side will be south, north pole, south pole, etc. Okay, so this is the correct explanation. When the north pole of the magnet is brought close to the paper clip, the tip of the paper clip will be induced with a south pole. So the keywords are already underlined, highlighted for you. And then since unlike poles attract, the paper clip will be attracted to the magnet. Okay, next one. Okay, so in this case, they say that a piece of wood is held between the north pole of the magnet and the two paper clips. Although wood is a non-magnetic material, the two paper clips are able to be attracted when the wood is held between the magnets and the paper clips. Suggests a reason for this. Okay, so you can see that the paper clips are not touching the magnet. Okay, they are separated by a layer of wood, which is a non-magnetic material, but the paper clips is still attracted, okay, to the wood. It still stay attracted through this layer of wood. Okay, this is because, okay, the solution is as follows. The paper clips are again magnetized by induced magnetism, or again, the tip of the paper clips gets induced with an opposite polarity, and it will still get attracted because unlike poles attract. Okay, you need to know that induced magnetism does not require physical contact. I do not need my magnet to be touching the paper clips. Okay, so the magnetic material only needs to be near the magnet. Since the paper clip is near, as long as it's near enough to the magnet, it will be able to be induced with our opposite poles. Okay, the next question is, it is observed that the bottom tip of the paper clip will point away from each other. Why is this so? So you must immediately know that if they point away from each other, it simply means that they are repelling each other. So I need to see the word like poles repel somewhere in your answers. Okay, so it is as follows. Okay, the paper clips have become an induced magnet, and the bottom tip of the paper clips are actually like poles, not poles, so they repel each other. So if you want over here, okay, let me draw for you. So if I have here like this, okay, this will be my south pole, my top, the end, the both ends, okay, nearer to the magnet will be induced with a south pole, and the bottom end will both be induced with a north pole. Like poles repel, so there will be repulsion here. Okay, at the top part, you will see that there is also repulsion. The paper clips do not stick exactly towards each other. There will be a gap in the center. Okay. Okay, next. Okay, other methods of magnetizing a magnetic material or making a magnetic material become a magnet includes the most commonly used one, which is called the electrical methods of using direct current. So what happens over here is you can take a look at this. I have a battery, and then I pass my battery into a coil of wire. So I coil up a wire that looks like this. So this coil of wire is called a solenoid. Okay, and I just place my magnetic material into this solenoid. Once I have electric current flowing through this solenoid, okay, the magnetic material that is placed inside this solenoid will become a magnet. So this is what we mean by using electrical method to magnetize a magnetic material. Okay, so you can read, whenever a direct current is passed through a solenoid, direct current only flows in one direction. Okay, there will be a strong magnetic field being produced near the solenoid. And then the steel bar or the iron bar that is being placed inside the solenoid will become magnetized, and it is then become what we call an electromagnet. It becomes a magnet when there is electricity passing through it. Okay, so some of the important things to take note: direct current only flows in one direction. Okay, because sometimes the question will ask for alternating current, or when we talk about demagnetization, we will be using alternating current. But for magnetization, we will be using direct current. Okay, and then a solenoid is actually a length of copper wire wounded into a long coil. And just take note, the copper wires are not bare copper wires, okay? They are actually insulated, so there's a layer of plastic covering them, but it does not affect its function. Even though there is a plastic layer around it, there is still a magnetic field being generated about it, okay? But we'll study about this in the next chapter on electromagnetism more in depth. Okay, so the strength of the electromagnet, how can we increase it? Okay, we can increase it by any one of these three steps. We could increase the current by adding more batteries, or if there is a rheostat that is attached to the circuit, we can decrease the resistance of the rheostat so as to increase the current flowing through it. The larger the current, more current flowing through it, the stronger the electromagnet, the stronger the strength of the electromagnet. Or we can increase the number of turns on the solenoid. Just take note, there are O-level is very particular. You need to mention is the number of turns on the solenoid. We do not accept like, oh, add more coils to the wire or increase the number of coils. Okay, it's always increase number of turns on the solenoid. Or we can insert a soft iron core to the solenoid. Okay, usually a soft iron, which we'll talk about it in the next part of in the part 2 of this magnetism videos, about the difference between soft iron and steel. Okay, soft iron is actually a very good magnetic material, so it's able to concentrate all the magnetic field into the soft iron core. So the soft iron core will actually becomes a very strong electromagnet in the center. Okay, next thing that is very important is you need to know how to determine the poles of the magnet that is being produced using this electrical method. So we will be using mainly the right hand grip rule. Okay, so how does the right hand grip rule works? I do not really like this picture. I like the next picture more. Usually we use method 1. Okay, we don't really use the second method, which I'll introduce to you. So how do we use right hand grip rule? Step 1 is called right hand grip rule because you'll be using your right hand. Okay, so you grip your right hand according to the photos like as shown. Okay, first step, we always trace the current flowing inside the solenoid. And when we trace the current flowing inside the solenoid, we always look at the current flowing in the front loop. Okay, we don't care about the current flowing at the back. Okay, so for example, over here, you can see my current is going up over here. So if one arrow is up, all the arrows will be up. So in the front loop is going up and then will flow downwards at the back loop and then up again at the front loop and then down again at the back loop and up again at the front loop. Okay, so we are only concerned about the direction of the current in the front loop. So you can draw your arrows. It's all going upwards in the front loop. Okay, and then next, use your right hand. Okay, I always say you grip it such that you can see your fingernails. Okay, the keyword is you must be able to see your fingernails. So there is only 2 orientation. Okay, so the first orientation is as this, and the second orientation is as this. So there's only 2 orientation of how you point your thumb when you can see your fingernails. Okay, so in this case, my fingernails always curl in the direction of the arrows at the front of my solenoid. So in this case, my first case, my arrows are all going up. My fingernails must be pointing up. Okay, so if my fingernails to have my fingernails pointing up or my fingers curl in the direction of the current, okay, it will be as shown in the first picture over here. So my thumb will be always the one pointing towards the North Pole. Okay, the thumb will always point towards the North Pole. So over here, I have the North Pole here and the South Pole here. And then you take a look at this case. Okay, at the back, the current is going up, but at the front loop, the current is going down. Okay, so the first step, I always identify the current flow in the front loop of the solenoid. Okay, so in this case, the current is flowing down. And then again, you grip your fingers. Now, your fingers must be curling downwards and you must be able to see your fingernails. Okay, so now the thumb is pointing in this direction. So this will be my North Pole. Okay, and the other end will be my South Pole. Okay, the second method of how to determine it, we seldom use it. Okay, so I'm not going to elaborate on it much. Okay, is by looking at the left end and the right end, the extreme ends of the coin, and then see how is the current flowing. Because I can't really visualize this. Okay, but if you could visualize this, you could also use this, but this is a little bit more challenging. So if you are looking at the left end, you will see that the current flows in a clockwise direction. So clockwise direction looks like this. So it's the South Pole. And then on the right end, it will be flowing in the anti-clockwise direction. So it looks like this. So it's the North Pole. Okay. Okay. You may pause the video here to think about the answers to this question. You are supposed to determine the poles. So I have a direct current passing through the nails and passing through the two nails and through the solenoid. So the two nails and the solenoid now becomes an electromagnet. You need to determine for me the poles of the electromagnet that is being produced, okay, by this direct current. Okay, I'm going to go through now. So for the first case, okay, I hope you are able to see the current will flow out of the battery. Let me jot down. Current will flow out of the battery in this way. So you should be able to see that at the front loop, okay, the current is all flowing up. Okay, flowing up, then to the back is going down and then back to the battery. Okay, so first step, always trace the current flow. I'm always interested in the current flow at the front loop of the solenoid. So if the current is flowing up, next step, use your right hand grip rule. Okay, you must be able to see your fingernails. Your fingernails must be pointing up. Okay, so you should be able to get the North Pole is on the left side and the South Pole is on the right side. Okay, let's take a look at the second one. Okay, second one, the current is flowing this way. Okay, so the current is going to flow up again. Okay, and then go to the back and down. So again, up is the similar as the first case. You have your North Pole over here and your South Pole over here. Okay, and then the third scenario, I have my nail in the vertical position, but the same steps occur. So the current is going to flow out of the plus side of the battery. We'll go to the back, and then you should be able to see that the current will be flowing down like this, and then going back to the battery in this way. So now your fingers must curl towards the right, and you should be able to see your fingernail. So it's like putting a thumbs up. Okay, your fingernails are to the right, pointing. You should be able to see your fingernails, and your fingernails are pointing to the right. Okay, so it's a thumbs up, and this will be, the top part will be a North Pole, and the bottom part will be a South Pole. Okay, so next, another method of magnetization will be by stroking. Okay, but we seldom use this, but this is also a way of magnetization. So you can see here over here, this is an unmagnetized steel bar. It's being struck with one pole of a magnet repeatedly. Okay, and just take note that you need to use the same pole to stroke in the same way each time. And the magnets must be lifted sufficiently high above the bar after its stroke. Okay, how do I determine the poles? Okay, the end that the magnet last leave, okay, will always be induced or will always be magnetized with an opposite polarity to the poles that is rubbing it. So the poles that is rubbing it is the North Pole, and the end where it last leave off is over here. So it will have an opposite pole. So this side will be the South Pole. Okay, you can take a look at this. So over here, I'm rubbing it with two magnets. Okay, so the first magnet is using a South Pole. The ends that it last stroke, okay, is over here. It will have an opposite pole over here. So this side will be North Pole. And then similarly, here is using a North Pole. So the end where it last touch is over here will have opposite pole. So it's a South Pole over here. Okay, next. Okay, we have more practice over here. You are supposed to trace the current flow or determine based on the magnet that's stroking it, what are the polarities. Okay, you may pause the video, but I'm going to go through the answers now. Okay, so the first step, okay, you should be able to trace the current flow for the first one. So the current is flowing out of the positive terminal. So it'll be flowing like this. Okay, this way. Okay, so you go to the back and then come to the front. So now all my arrows are pointing to the left. Okay, so using your right hand grip rule, you must be able to see your fingernails, and your fingernails must be pointing to the left. Okay, so this is a bull sign, if you get it. Okay, lousy bullseye. Okay, your fingernails are all pointing to the left. Okay, you have your thumb pointing downwards. Okay, so the bottom part will be the North Pole and the top part will be the South Pole. Next, okay, you have a bar magnet being stroked like this. Okay, the South Pole is being used to stroke, and the last part that it leaves is this area. So this area will be North Pole, and the other end will be at South Pole. Okay, next over here, North Pole, the ends that it leaves is here. So this end will be a South Pole, and then South Pole is used to stroke this side. So the end that it leaves will be a North Pole. Okay, and then next, again, I'm supposed to trace the current flow. So current is flowing up like this. Okay, this part, if you can see at one side, for example, this side is very hard to see. I will see by the other side. So the other side, the current must be flowing up like this. Okay, and then go here and then go back to the battery. So over here is all up. Okay, and then using your right hand grip rule, okay, your fingernails facing you and your fingernails must be pointing up. You have your North Pole on the left side. Okay, your thumb is pointing to the left. Okay, next question. Suggest one way to reverse the polarity of the electromagnet being produced. So for example, in this case, the first step, okay, they have already traced the current flow for you and the current at the front part of the solenoid is all facing down. So using your right hand grip rule, okay, you should be able to get a North Pole here and a South Pole here. Okay, so now I want to reverse the polarity. Means I want the right side to be a South Pole and the left side to be a North Pole. I want to change the poles. So how can I reverse the poles? Okay, very simple. I just reverse the poles of the battery. Okay, reverse the polarity of the battery. Because if I reverse the polarity of the battery, then the current will all be flowing up at the front loop and the poles will again, the poles will be changed. Okay, so I just reverse the direction of the current flow by reversing the polarity of the battery. Next day, suggest 2 ways to decrease the strength of the electromagnet. So this is an electromagnet. When I close my switch, got current flowing through it, it becomes an electromagnet. So how do I decrease the strength? Okay, you can see over here, there's a rheostat. I can increase the resistance of the rheostat, okay, to decrease the current flowing through it. Or I can decrease the number of turns of the solenoid, or I can remove the steel bar. Okay, even if there is no iron bar, no steel bar inside it, okay, there will still be a magnetic effect. It will still becomes a magnet over here, even without the iron bar and the steel bar. But if I place a magnetic material like iron bar or steel bar inside this solenoid, it will make it becomes a stronger magnet. So I don't want it to be such a strong electromagnet. I can just remove my items inside, be it an iron bar or steel bar. Okay, so these are the few methods. Okay, you can just choose any two. Okay, so summary, there are 4 properties of magnets. A freely suspended magnet will always come to a rest in the north-south direction. It always has 2 poles, and the magnetic field strength is the strongest at its poles. The 2 poles are the North Pole and the South Pole. Next one, like poles repel, unlike poles attract, and magnets is able to attract magnets as well as magnetic material. So repulsion is the only test for magnets. To confirm that 2 items are magnets, there must be repulsion. Okay, next we also talk about induction or induced magnetism. It takes place whenever a magnetic material is placed close to or touching a strong magnet, or it is placed within a current carrying solenoid. Okay, it will also result in an induced magnetism or induction because it only becomes a magnet when there is current flowing through it. When a current is switched off, it will not become a magnet again. Okay, it will not be a magnet anymore. So these are all induced magnetism. Okay, that's all for the first part.